funded PhD with Newcastle University, and that's part of a 3-year funded project focusing solely on image velocimetry techniques. So the motivation behind this chapter was just to give an introduction to velocimetry to those who may not be all too familiar with the techniques. So I've started by looking at generalized processes, and the aim of the review is to present and discuss some of the key challenges and considerations that you need when you're trying to acquire image velocimetry data within a fluvial setting.
I think it's just stopped, is it?
You might have to press the button slide to move to the next one.
So to do that, I decided the easiest way was to break down the full process into 4 key stages that most generalized studies will go through. So the key stages that I defined previously have been broken down a little bit further so that I can talk about the specific processes. I'm just going to touch on some of the most important pieces of research that I found just to try and help people optimize their workflows whilst they're trying to use image velocimetry techniques like PIV and PTV. So starting with stage 1, capture optimization. It's been further broken down into 4 subheadings, starting with ground sample distance, or GSD for short. As I discuss each of these subheadings, I'm going to try and go into a little bit of depth about what they actually mean for velocimetry, and I'm going to provide some figures and diagrams where possible. So to start with, we're going to look at GSD, which I previously said is ground sample distance, which is simply the distance between the centroid of 2 adjacent pixels. Typically, this ranges between 0.02 meters through to satellite imagery, which can be tens of meters. So without changing hardware, there's actually 2 main ways of improving GSD. That's either decreasing the distance between the camera and the subject site or increasing the resolution of the imagery. Regarding the height, it depends on whether you are using a fixed camera or a mobile camera. So fixed cameras can be complicated to install and optimize in terms of the angle and the height. This very much depends on the level of access that you've got on site. Mobile stations, however, are very flexible regarding their height and therefore should be optimized to fly as low as possible while still capturing the full study area constantly. For fixed stations, it may not be able to greatly reduce the height of the camera. Sometimes zoom lenses can be used to increase the focal length of the camera, which can have the same sort of impact. One thing to quickly note here, however, is the possibility of the stage increasing in the rivers with fixed cameras. A large increase in stage can actually hinder the viewpoint of the camera if it's too low down with a narrow angle, because it will just shrink down the area that the camera can actually see. There's little in research in the way of defining the best resolution to use on sites, but there's actually quite a lot suggesting that increasing the resolution doesn't always necessarily improve your results. Research does state that increasing the resolution severely increases the processing time as well as your storage requirements. It's actually quite hard to suggest an optimization of GSD. So this is a couple of equations that you can use to determine GSD with or without angles. They can be really useful when you want to work out the height that you need to set the camera to achieve a certain GSD. The equation on the left are for cameras that are stationed with a nadir angle, while on the right you can introduce 2 angles, one in the horizontal and one in the vertical direction. So the equation on the right splits it into a gridded system of 4 quadrants and gives you the average value across that quadrant. To see how they work, check out the next slide with this simple tool. So this is the tool that I created on the spreadsheet. It's available on GitHub, and it just adds an angle to a camera, which helps you describe the GSD in the 4 quadrants. It's still a little bit of a work in progress, but it's still decent enough to help you understand the general gist of how things impact GSD. So moving on to traces, research says that for good practice, traces need to be present on at least 10 to 30% of the surface of the river. It needs to remain visible and traceable throughout the sequence. Sometimes where studies aren't continuous and traces aren't prevalent, you can actually use artificial traces such as bark or decomposable polymers, so long as they're passive to the flow, easily distinguishable, and they have no effect on the water quality. For a tracer to be good, it must be stable in shape and size over the time of the sequence. It should also be larger typically than 1 pixel of the image. For artificially placed tracers, the ideal particle should be ellipsoidal and between 2 and 5 pixels, as they've been shown to perform best. So for standard video cameras, the capture rates during the capture optimization stage isn't actually much of an issue, because most cameras will actually capture at least 15 frames per second, which is more than enough for image velocimetry techniques. The key to capture rate during this stage is to ensure that the frame rate is consistent throughout the video sequence. Usually that's not much of a problem because a lot of video cameras supply a timestamp to each of the frames, so you can double check it. There's no real limit on what type of video camera you can use to capture the imagery, but it should be noted that video sequences can actually take up quite a lot of storage space, especially with raw imagery. So you can use things like IP cameras, but you also have to then consider the constraints that you have regarding things like bandwidth of transferring the imagery. Finally, for capture optimization, it's important to consider the environmental conditions at the time of capture. So some of the environmental conditions that I focus on is the presence of wind, rain, and glare within the imagery. Although they've been mentioned in previous studies and case studies as limiting factors, there's little to no research in actually quantifying the impact that they have on the results, and they're usually limited by not actually being present in the data used for a majority of case studies. Some of the typical factors that I have hypothesized to be associated with the environmental conditions are for wind, you've got false traces and tracer disruption. Rain, you'll have blurring of the imagery, false vectors and tracer disruption. And finally, for the glare, the impact that brightness variation has across the image and the loss of traces. And that's just to name but a few. So part 2 is the pre-processing stage, and that includes image stabilization, orthorectification, and image manipulation. For image stabilization, there's two main methods, and that's either manual or automatic. For manual methods, it relies on a selection of static reference points, which are then automatically processed to determine the displacement between frames. Or for automatic methods, the features and the displacements are both selected and tracked using binary feature matching techniques. For most stabilization transformations, you need at least 4-point pairs for a full projective transformation, but that also takes into account the perspective deformation. It's also worth to note that if there's a vast amount of movement between the frames, the programs can actually be set to update the reference frame per number of frames, or you can simply use the first frame as its point of reference. Without a sufficient stabilization, then displacements can be really skewed, and even stationary objects can be detected as moving and then given a velocity vector. Another important stage of pre-processing is orthorectification. This can be done at a later stage, however, we're going to be looking at explicit orthorectification, which is simply applied to raw video footage instead of later applied to the velocity results, which is implicit orthorectification. The only time that orthorectification isn't required is when data is actually captured perfectly to nadir and the intrinsic image distortion from the camera has been completely removed. So there's two different types of orthorectification that can be applied depending on the location in the camera and the number of ground control points available. So if there's 4 GCPs at the river surface elevation, then you can perform a 2D transformation which has an 8-parameter plan-to-plan perspective. For 3D transformations, they can be made when there's a large variation of elevation between the GCPs and the river surface. If that's the case, then a projection has 11 unknown dimensions and can only be solved with 6 or more ground control points. In general, it's actually suggested that a minimum of at least 4 GCPs should actually be used in or around the immediate region of interest, and that's to achieve the best results. So image manipulation isn't actually a step that's always required. The importance of it is when traces aren't as prevalent as they could be and programs have a problem detecting or tracking them throughout the process. There's several different techniques that you can apply to imagery to enhance the tracer visibility. There's a few of them on screen, but one of the most important techniques to use arguably in most cases would be enhancing the imagery through contrast enhancement steps. That's just simply enhancing the brightness between the tracer and its background just to make it stand out a little bit more throughout the process. In general, as an absolute minimum, I think it's suggested that an imagery is converted to grayscale and then cropped to the area of interest just to reduce the unnecessary data processing and the noise wherever possible. So the figure that you can actually see on the screen employs each of the corresponding enhancement steps that you can see on screen to a video frame that's been captured from a drone roughly half a second apart. So the top figure is the raw image simply grayscaled. The middle section shows how each individual enhancement step affects the imagery. And then the bottom band actually shows how applying mixed enhancement steps can greatly improve the tracer visibility against the river surface. For part 3, I'm just going to talk about the founding principles and the feature tracking schemes for the processing stage. I'm not going to go into too much depth with the foundations of velocimetry, but the general gist of it is that Eulerian motion is used within PIV methods and Lagrangian motion defines PTV methods. So Euler uses a fixed area to determine movement between the grids and the particle displacement, whereas Lagrangian tracks the individual particles throughout the frame, and there's no real way of predetermining which technique is going to be better, as both of them have their advantages and disadvantages. So there's a limitation with Lagrangian techniques, as they have natural traces that aren't entirely stable in structure, and they're capable of deforming, breaking up, agglomerating, and they interact with one another. The problem is we're not yet able to define how those particles interact with one another mathematically. A limitation with Eulerian, however, is the reliability of the particles to remain steady throughout its gridded structure in terms of velocity, and that's just a basic fundamental to do with the mathematics and the assumptions that it makes. This takes me on to looking at actual feature tracking schemes such as PIV and PTV. I've previously said that PTV methods rely on the tracking of individual particles, and that's a long profile. And they normally form well under low seeding density conditions. And then on the flip side, you've got PIV methods, and they use search and interrogation areas within an image to obtain particle displacements. And they're a lot less sensitive to like transformation of individual features. And they can also deal with much larger seeding densities. Problems consist there, however, when there's inhomogeneity and there's a discontinuity of traces. One thing to bear in mind is actually especially with PTV methods, the greater number of traces that are successfully tracked, the higher the probability of producing an accurate representation of the surface velocity. But then on the other hand, and as the number of traces increase, you've got a higher required processing time and power. Typical feature detection methods are good features to track, sift, and fast. The tracking algorithms cross-correlation can be used, but there's also others such as the KLT algorithm and variations of the nearest neighbor algorithm. Once the processing of the data has been accomplished, we can then move on to the post-processing stage and either correct the data should it need to be or begin to apply the data. Finally, we've got the stage 4, and it's the post-processing stage, which is broken down into two subheadings as error statistical analysis and discharge calculations. For the error analysis of data, it's important to consider two things: the detection of the erroneous data and then the replacement of the data. Good practice would have each output dataset checked for spurious vectors and corrected. Most commonly, a 2D interpolation is used, but a linear or polynomial interpolation can also be used. I'm not going to go into too much depth on how to perform those analyses. However, should you want to know more, I do provide some common statistical corrective methods for both PIV and PTV. The ones for PIV are penalized least squares method, the Kriging regression, and proper orthogonal decomposition outlier detection. For PTV, the universal outlier detection scheme or model-based techniques such as Young's study in 2004 showed to validate data that has up to 25% of outliers. To determine discharge from the velocity outputs, it's important to estimate the average depth velocity for a specific cross-section seen within the imagery. Usually, to calculate the depth velocity, an alpha coefficient is usually required, and normally it's estimated to be around 0.85. To determine the area required for discharge calculations, it's required to introduce a known measured transect that coincides with the camera's field of view. This can be done by surveying where appropriate, or alternatively using an ADCP, again where appropriate. One issue that may be seen while trying to calculate discharge through image velocimetry techniques is that the river surface must also have a good spread of traces, and where that's not possible, in the case it might be possible to interpolate or extrapolate measurements using polynomial cubic or the constant Froude method. That brings me to the end of the literature review and brings me on to my key findings. So it's safe to conclude that there's a vast amount of research regarding the optimization for most parameters, with traces, angles, stabilization, and orthorectification being key considerations for reliable processing. However, there's not a clear optimization for resolution. On the other hand, there's a lot of precedents to suggest that the users need to use their intuition to decide on the best resolution for processing, speed, and tracer quality. The most important finding from this study is the lack of information around how to process the imagery that's heavily influenced by environmental factors such as wind, rain, and solar radiance, or brightness variation. This is something that I plan to look at further in the next coming months. That's everything from me, and if you need any more about the work that I'm doing or what I plan to be doing later on, please feel free to drop me an email and I'll get back to you as soon as I can. Thank you for listening.